Hello everyone, my name is Amir Jafari, and this is our brief announcement for SPAA 2020 with the title Local Constant Approximation Factor Algorithms for Minimum Dominating Set of Certain Planar Graphs, which was done jointly with Sharareh Alipour. The concept of domination is one of the most important concepts both in theory and applications of graph theory. It has applications in robotics, networking, and wireless communication. In this work, we propose a local constant approximation factor algorithm for minimum total domination problem for planar graphs without 4 cycles. A dominating set, respectively a total dominating set for a graph G, is a subset S of vertices of G with the property that any vertex not in S, respectively every vertex of G, has at least one neighbor in S. The dominating number gamma of G, respectively total dominating number gamma t of G, is the size of a minimum dominating, respectively total dominating set for G. It is easy to show that gamma of G is less than or equal to gamma t of G is less than or equal to 2 times gamma of G. The algorithm that we propose is a very simple greedy algorithm. Every vertex picks the neighbor with maximum degree. The chosen vertices clearly give a total dominating set. So this works for any graph. There is a small problem. What if a vertex has several neighbors with maximum degree? This problem can be resolved in 2 ways. One can either use the vertex identifiers and pick among the neighbors with maximum degree the one with maximum identifier, or each vertex V chooses a random real number R of V between 0 and 1 and sends its weight, which is R of V plus degree of V, to its neighbors. Now the weights are almost certainly distinct, and each vertex picks the neighbor with maximum weight. Although this algorithm works for any graph and produces a total dominating set, the approximation factor can be only handled for very particular graphs. We were able to show for planar graphs without 4 cycles, the size of the total dominating set returned by this algorithm is at most 9 times gamma t of G, and hence is at most 18 times of gamma of G. So this is the approximation factor for total dominating set is 9, and the approximation factor for dominating set problem is 18. It was previously known that no local algorithm can solve minimum dominating set problem for planar graphs with an approximation factor less than 7, and the best approximation factor for the local algorithm that solves this problem for planar graphs is 52 if we have identifiers, and is 636 without identifiers. Now in the remaining time, I want to give you an idea of the proof of this analysis. First, we order vertices V1 up to Vn so that the weights are decreasing. Assume the algorithm returns V of L1, V of L2 up to V of Lk as the answer, and let xi be the number of vertices that pick V of Li. We also use the notation n of S to be the set of vertices adjacent to at least one vertex in S, where S is a given subset of vertices of the graph G. The first observation is the following lemma. For any number m between 1 and k is the number of the vertices returned by the algorithm, we have the size of the neighbors of V1 up to Vm with this order is less than or equal to the sum of xi's from 1 to m. The proof of this is very easy and works for any graph with no hypotheses. The second lemma, which is very critical and crucial for our work, is a lemma that works only for planar graphs without 4 cycles. Let S be a subset of its vertices, then the claim is that the size of n of S is always less than the sum of degrees of vertices in S minus 8 times the size of S. The proof of this is done by observing that the size of this n of S, which I denoted by U, is equal to the sum of degrees of the vertices in U minus this number that is in the sigma. So which means that some of the vertices are counted many times and we have to remove these multiple counting. Now we have to estimate the second sum, and this is done by the fact that the number of edges in a planar graph is less than 3 times the number of vertices in this graph. And I'm not going to go through the details of the proof, but however, I should mention that it is done by constructing an auxiliary planar graph. Now, once we have these two lemmas, the proof of the approximation factor is relatively easy. Let U1 up to Un be a minimum total dominating set, and suppose that we take V1 up to Vm, the first m vertices with the highest weights, and we want to count the number of adjacent vertices to one of these vertices. We have an upper bound, we have a lower bound using the two lemmas, and if we compare these two bounds, we get the following inequality. And now if you play with this inequality and use the fact that the sum of xi is equal to n and xi's are bigger than or equal to 1, we arrive to the second inequality that says that the sum of xi's from 1 to n is at least n minus k minus n, and we're putting all together, we get the results k less than or equal to n. Now, the idea of the proof of the second lemma works best for planar graphs with no 4 cycles. However, it can be modified to work for planar graphs with few 4 cycles relative to the number of their vertices. And for a tree, one can show that the approximation factor can be reduced from 9 to 2. Thank you for your time.